Alright, so I want to move on to slightly more complicated examples. Let's ramp up that last one. The last one we did in the last video was the probabilities surrounding a fair six-sided die. So I want to just make that sort of the next most complicated thing that I can do. I suppose the next most complicated thing I could do would be to roll a six-sided die and flip a fair coin. But I'm going to jump to two fair six-sided dice. And one interesting thing that you can do when you roll two fair six-sided dice is to look at the sum of what's showing. And so I just have a box here. Let's figure out the probability of obtaining a sum of something. All right, so we're gonna do them all as we go. That is a horrendous question mark. That's a little better. A sum of whatever. All right, so we're gonna figure out what are the plausible sums here, and we're just gonna figure out the probabilities of all of them while we go. Okay. Okay, so what we're going to do here is we are going to imagine rolling these two dice, and the first thing I want to do is let's figure out the sample space. All right, so this is the set of possible outcomes. All right, and what are the possible outcomes from rolling two six-sided dice? And then adding, right, so a sum means you add them, and then adding the results. All right, so think about the smallest result you could possibly get. The smallest outcome you can possibly get out of these two dice would be if you happen to roll a 1 and a 1, right? That's the smallest thing you could possibly have, meaning a sum of 2. All right, now think to yourself, is it possible to get a sum of 3? The answer is yes, a 1 and a 2 would do that for you. Is it possible to get a 4? Yes, a 3 and a 1, or a 2 and a 2. It's possible to get a 5, 6, 7, 8, 9, 10, 11, and now we're up at the highest one. 12 would be the largest possible outcome, because that would require a 6 and a 6, and that is maximum output on both of the two dice. Alright, so this is our sample space here, the integers between 2 and 12. Now, this is a set of all possible outcomes. So what I don't want you to do at this stage is to say, let's ask the question, what's the probability of rolling a 5? Right, so you look at this sample space and you say, okay, hey, there's a 5 right there. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible outcomes. 5 is one of them, so this is going to be 1/11th. That is extremely false. Not even close. All right? So this is one pitfall I do not want you to succumb to. All right? Just looking at the sample space and saying, well, it worked for every other example, is not going to cut it here. And I will show you why that is. All right, so this is 100% false. All right, this logic will not work at all for this example. And the reason why is that some of these outcomes are much more likely, or, if you like, much less likely than others. All right, I'll give you a very quick example. When I was listing out all the different ways that that something can occur here, right, I was listing out all the different sums that are possible. I said, a 2, well, this has to be a 1 and a 1, right? A 1 on both dice, rather. And I said, I think a 4 could be a 3 and a 1, or it could be a 2 and a 2. Right there, that tells you that a 4 has to be more likely than a 2. Why? There are multiple ways that a 4 can occur, and there's precisely one way that a 2 can occur. Alright, so these are not going to be equally likely outcomes. Alright, these are not equally likely. This means that we're going to have to do more work. Okay? So even though both of the two dice are fair, which means that there's an equal chance of getting a 1 or a 2 or a 3 or a 4 or a 5 or a 6 on each one of the dice individually, once you start looking at something like a sum, all of that equal likelihood stuff goes by the wayside, because now you've got a much more complicated thing to address. And this arises because there are multiple ways of combining the outcomes on each fair die to get a different sum. Okay, so this is really the idea. So we need to run through this. Let's just go one by one here until we figure out some patterns. How many ways are there of rolling a sum of 2? Well, this has to be a 1 on die 1. All right, let's do it this way. There's die 1 and there's die 2. Has to be a 1 and a 1, right? This is the only way to get a sum of 2 out of this. This means that there is precisely one way that this can occur, right? Die 1 has to be a 1 and die 2 has to be a 1. That means that there is one way that you can throw both of these dice simultaneously and have it show up as a 2 sum. Alright, how about a 3? Well, let's say die 1 rolls a 1, die 2 rolls a 2. This gives you a sum of 3. Now you have to ask yourself this question. Is this the only way that this can occur? Hopefully, you agree with me that this is not the only way this can occur. It could have been the other way around. Right? Die 1 could have been a 2. Die 2 could have been a 1. There are 2 ways this could have occurred. All right, let's look at a sum of 4. Die 1 could be a 1. Die 2 could be a 3. Die 1 could be a 2. Die 2 could be a 2. Are these the only 2 ways that this could have occurred? Hopefully, you agree that the answer is no. Same thing could have happened where we do the old switcheroo. Right? Die 1 and die 2 could have been a 3 and a 1. Notice that if I did the old switcheroo, as I just called it, with the 2 and 2 example, they both still read 2 and 2. That's not a different outcome, right? They both still say 2. But think of it like if you had a red die and a green die or something. If the red one, let me do it in these colors. Right? If the red one comes up 1 and the green one comes up 3, well, that is a different outcome than if the red one had come up 3 and the green one had come up 1. However, it is the same outcome as if both are showing 2s, right? Switching them, they still both say 2. Whereas these other ones are fundamentally different, right? The dice show different results. So, there are 3 ways that this could occur. And hopefully you can sort of see the pattern, sort of start to guess what the pattern might be, I should say. If we do 5, that might make things clearer. Let's have die 1 and die 2. So a die 1 could show 1, 2 could show 4, die 2 could show 2, die 2 could show 3, and now we need the mirror images of all of these. 3 and 2, 4 and 1. And there are 4 ways that this could have occurred. 6. If you had to guess, right? If you had to put money on it, 1 way, 2 way, 3 ways, 4 ways, you're probably going to guess that this would be 5 ways that this next one can occur. And you would be correct, right? So you could have a 1 and a 5, 2 and a 4, 3 and a 3, 4 and a 2, 5 and a 1. There are 5 ways that this can occur. And 7. Let's see here. Guessing, right? The next one, probably a 6, right? 6 ways that it can occur, that is. So 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. There are 6 ways. Now, hopefully you recognize that we have hit a sort of important stopping point. Not a stopping point, but an important critical point, like a point where things change. Because we now require that the numbers are bigger, right? So we've sort of hit the point where starting with a 1 on one of the dice, it will require the maximum output on the other dice, on the other die. And so we have to have hit like the top of the mountain, so to speak. 6 is going to be the maximum number of ways for any of these outcomes to occur. Because if we have this die 1 as a minimal number of 1, well, die 2 is already maximal, telling us that the biggest way this can occur is with a 7 as the sum. All right, so we expect that this increasing pattern, right, it increased from 4 to 5 to 6, that's got to be stopping growing. It cannot grow anymore because we've sort of hit this this critical juncture where a minimal result on one die requires a maximal result on the other to give you the sum in question of 7. So that's maybe a little more analysis than you really need. When all is said and done, you can just keep counting these things. Let's see what happens. So result of 8 is the last one I'm going to do. Let's just keep digging this hole deeper and deeper. That's a terrible 8. Darn it. Let's fix that. 8. All right, die 1, die 2. Okay, so now the smallest possible outcome on die 1 that can even make an 8 possible is now a 2, right? A 1 would make it impossible because you can't roll a 7 on the other one. And that requires 6, or you could have a 3 and a 5, 4 and 4, 5 and 3, 6 and 2. There are 5 ways that this can occur. And I mentioned this is the last one I'm going to do because hopefully you start to see the pattern here. If I sort of do this out graphically, what was the maximum? It was 6, right? So 1, 2, 3, 4, 5, 6. My y-axis here would have to be number of ways that the sum can occur. And my x-axis would have to be the sum of the 2 dice. Just to give you a visual, a little visualization of what's going on here. 2 is the smallest sum possible. 3, 4, 5, 6, 7, 8, 9, 10, 11, make it a little longer, 12. Alright, so what we've seen here is that, also I should label these, 1, 2, 3, 4, 5, and 6. Alright, what we've seen is that 2 occurs in precisely one way. A 3 occurs in 2 ways. Right here you can obviously work it out again if you don't believe me, or just pause it and rewind a little bit to see how these ways were worked out. I'm not just making this up. This is not magic. This is stuff we just did. 4 could occur in 3 different ways. A 5 could occur in 4 different ways. A 6 could occur in 5 different ways. And a 7 is the most likely. It can occur in 6 different ways. And now we just saw that an 8 occurs in 5 different ways. A 9, just extrapolating, you can work it out, obviously. It would be a 6 and a 3, a 5 and a 4, a 4 and a 5, a 3 and a 6. So that's 4 different ways. 10, 3 different ways. 11, 2 different ways. 12, 1 way. 6 and 6, that's it. Alright, so we get this really beautiful bar graph. It's not beautifully drawn, right? This is not visually pleasing, but this is a very interesting pattern. And it's, I didn't work out the last ones, right? I stopped at 8, so these, check those yourself that you do actually get those. I quickly ran through 9, so hopefully you believe that one. And I told you what 12 is, so that really only leaves 10 and 11 to check. However, this tells you a sense of the distribution of what's going on here, right? Not all of these outcomes are equally likely. So if I jump back a few pages to our sample space, which is right here, sure, there are 11 outcomes in the sample space. However, they are very lopsidedly distributed in terms of their likelihood of occurring. Right, looking at this little graphical visualization of the data, 7 is the most likely thing to occur, followed by 6 and 8 would be the next most likely, followed by 5 and 9, then 4 and 10, then 11 and 3, and then 12 and 2. All right, so let's use this funny little bar graph to start quantifying these probabilities. All right, so from the bar graph, what is the probability of rolling a sum of 2 on 2 dice? Well, look at the bar graph to tell you how many different ways that event can occur. And that is 1 way, right? This can only happen if it's a 1 and a 1 on the 2 dice, respectively. So that can happen in one possible way. And now, here's where you have to be super careful. The number of events now, since they're not all equally likely, the number of events is not what we're going to be measuring our likelihood out of, right? This would be like putting an 11 on the bottom, like I did at the very beginning of this video, which I said was horribly wrong. So what we need to look at down here is how many ways can 2 dice be rolled. Right? In other words, how many different ways are there of obtaining absolutely any sum on 2 dice? And notice that this is, the way I'm asking this question should sound reminiscent of something that we did relatively recently, about a month ago, a little over a month ago. This should sound like the definitions of pivotal players leading to the Shapley-Shubik power index and critical players in the Bonzhoff power index. Right, the way we defined those was the number of times that a player is critical divided by the number of times anyone is critical. So what we're really asking here is how many different ways can a 2 be rolled, a sum of 2 be rolled? The answer is 1 way. Right, it has to be a 1 and a 1. How many ways could anything have been rolled? Well, now we need to do a little bit of work. You could either take the heights of each one of these bars in the bar graph and add them all up, or you could be cleverer about it and use all of that combinatorics that we just spent a while building up. You have 2 dice that you are trying to roll. How many outcomes are there on the first die? Well, it's a 6-sided die. So there are 6 outcomes possible. How many outcomes are there on the second die? Well, it's also a 6-sided die, so there are 6 more outcomes. How many outcomes are there total? Right? So you're viewing these dice as like 2 decisions that you have to make. Decision 1 is rolling dice 1, or die 1. Decision 2 is rolling die 2. How many different ways are there of doing this? Well, fundamental counting principle tells us there are 36 ways that these 2 dice could be rolled together. And when I say ways, I don't mean like, fancy ways of shaking your hand before throwing the dice. I don't mean like that. I mean that you roll these dice, and there are 36 different options for what the outcome will read. Like 1-1 versus 1-2 versus 2-1 versus 2-2 versus 3-1 versus 1-3. Right? These are all different outcomes. This is what I mean when I say ways. All right, so fundamental counting principle tells us that there are 36 possible outcomes here, meaning that the probability of a 2, rolling a sum of 2, is 1/36. All right, let's jump around a little bit. Let's not go in order. Let's say the probability of rolling a 5. All right, what's the probability of rolling a 5? Well, a 5 occurs in 4 different ways. And there were 36 ways that anything could have occurred. So the probability of rolling a 5 is 4/36. This is 1/9 if you like reduced fractions, which I know you do. How about the most likely? All right, what's the most likely one here? It's a 7. How many ways were there? 6. Probability of rolling a 6. 6 ways out of 36 ways any combination could have been rolled. This is 1/6. All right, and you could fill in any of these other ones as you like. Let's do maybe 11. All right, I'm just grabbing random ones here. There are 2 ways that this could have occurred, 5 and a 6 or a 6 and a 5. So the probability of an 11, 2/36, reducing 1/18. All right, so this is the idea here. Now, if we wanted to make this, sort of ask and answer the same kinds of questions that we did before, like for instance, what is the probability that you roll a sum that is even? Right? This is a question that you could ask. What is the probability that you roll a sum that is bigger than 9? This is a question you could ask, right? What is the probability that you roll anything other than a 4 as your sum? Right? These are all questions that should be answerable, right? We should be able to come up with answers for these. Let me just jot those down, right? So what is the probability of rolling an even? What is the probability of rolling, of the sum being bigger than or equal to 9? What is the probability of the sum just not being 4? Right, as a totally random example. I'm making these up. We should be able to answer all of these questions, all right? And to do these directly is certainly possible. It can become extremely tedious. So for some of these, there are going to be ways that we can attack it that are, a little more methodical, a little more, clever, tricky. I don't want to use words like that because those are intimidating words. Because, if you feel like you're not a math person, then you probably feel like you're not a clever math person, which is ridiculous. You all have cleverness in your own ways. So I don't want to use words like that. I want to just give you a better tool set than the direct approach, right? I don't want everything to be direct counting stuff, because that can be very tedious, as you've seen. All right, so let's look at evenness. All right, what's the probability of being even? Well, this means that you are a 2, or a 4, or a 6, or an 8, or a 10, or a 12. That's a little cumbersome to write out, but there it is. If I jump back to my bar graph, 2 occurs 1 way, a 4 occurs 3 ways, a 6 occurs 5 ways, an 8 occurs 5 ways, and so on, right? I could do it this way. 2 occurs 1 way, 4 occurs 3 ways, 6 occurs 5 ways, 8 occurs 5 ways, 10 occurs 3 ways, 2 occurs 1 way. And again, I'm adding because of this all-important word, or. Right? Or is an inclusive thing. You're adding on possibilities by saying this or that. More than one way that something can happen. And this should be divided by the number of ways anything can happen, which is 36. Alright, so adding these numbers up in the top here, this is 1 plus 3 is 4, plus 10 is 14, plus 4 is 18. This is 18/36, and that is 1/2. Makes sense, right? Look at all the numbers between 2 and 12. Well, I shouldn't just directly say that makes sense, because there are more even numbers in there than there are odd numbers. However, this is the weirdness of the fact that these things are not equally likely to occur, because if you look at the most likely to occur, it's a 7, which is an odd number, but there are fewer odd numbers in there, and they're sort of balanced out by being more likely, or having the most likely one being an odd number. Anyway, so this tells you that the probability of an even should be 1/2. Now I want you to notice something else as well. If we were to split this up, right, this gigantic fraction here, if we were to split that up into a bunch of little fractions, what would happen? This would look like 1/36 plus 3/36 plus 5/36 plus 5/36 plus 3/36 plus 1/36. And if you remember, or if you worked it out on your own, this is the same as the probability of a 2 plus the probability of a 4 plus the probability of a 5. I'm sorry, not a 5. I've lost my mind. A 6 plus the probability of an 8 plus the probability of a 10 plus the probability of a 12. In other words, this or turning things into adding seems like it turns the ors being inside of a probability into a giant sum of probabilities. And this is true in this case. Not always true, we have to be careful, but it's true in this case. Alright, so that's interesting. I'll write this here as a question. Is it always true that probability of A or B is equal to the probability of A plus the probability of B? It's a question at this stage. Is it always true that this is the case? The answer is likely no, because I'm asking it as a question, and it's a leading question, and I just threatened you. So, this is not a fact, okay? It seems like it's true in this one case. We're going to have to do some work to see that it's not. All right, the other thing I want you to see here, let me look at, okay, so I did probability of evens, and we found it to be 1/2. It's a probability of evens. It's 1/2. What is the probability, what is the probability of odds? Wouldn't it be nice if we didn't have to do any work to figure this out? Right? Intuitively speaking, if the probability of evens, if it's 50% chance of getting evens, intuitively speaking, I would say it makes sense that the probability of odds should also be 50%, right? It should be equally likely. This is using the idea of what's called a complement. Not a compliment, like something nice someone says about you. This is a complement, like everything else that's out there, right? A complementary thing, meaning it fills in the gaps, so to speak. So, the probability of a complement, that little C up there means complement, well, this is going to be absolute certainty minus the probability of that event occurring. All right, so for instance, probability of odds is probability of the complement of evens, because everything that's not even must be odd. And this is going to be 1 minus the probability of evens. We know the probability of evens is 1/2. So this is also 1/2. There you go. Quick proof.